Good evening, everyone. Well, I'm recording this in the evening, so hi, whatever time of the day you are watching this. This is an introductory lesson to some terms regarding energy changes in chemical systems. So we'll try to keep it brief, just in case you're watching this as a review and you've seen most of the introduction to this already. So energy changes are important because they'll allow us to interact with transfers of what we know as heat. Right? So we'll look at the technical term for that and how it applies to chemical systems, which is basically a chemical reaction. Okay, so keep that in mind, that a system is a reaction as we go through this unit. So by manipulating these chemical reactions, we can manipulate energy being released or storing energy, which is pretty key to our society, right? When we drive cars, we release energy into the engine, which allows work to be done on the car and causes it to move. And there's also situations where we try to store energy away for later use. So we'll look at ways that we can do that. So to begin, we'll look at our learning objectives for this little lecture here. And we want to describe terms related to energy that you see there. We'll go through all of those. We'll identify what the surroundings of a chemical system are and why they play an important role in the chemical system. We want to be able to differentiate between exo and endothermic processes. If you've never seen those words before, don't worry, we'll recap those here. We want to be able to describe energy changes related to phase changes, which are a physical process. Right? And then lastly, we want to be able to interpret potential energy diagrams which is a little more theoretical here. So here's a demo that you could try at home if you had these substances safely. 0.5 grams each of those substances you see mixed in with each of those. So if we were together, we would design a small procedure to actually try this. And this is one of the mixtures that ice packs are. And you know that when the reaction happens in an ice pack, it gets cold. Right? So if we think about absorbing or releasing energy as a reaction, what happens here, because it gets cold, it's absorbing energy from you. So your hands perceive a lack of heat, and that tells your body that, hey, it's cold. On the other hand, if it was releasing energy, your hands would be absorbing that, and your brain would think it's hot. So there's a way that the nervous system interacts. Right? So let's get into the technical terms. The law of conservation of energy, there's many facets to it. Essentially, it says energy cannot be created or destroyed, only transformed in the various forms that we know. So we have examples like electrical energy to light energy and thermal energy when we turn on a flashlight. Right? The little bit of heat that gets generated is a type of energy that's a waste energy. We also have kinetic and potential energy. So an apple hanging on a tree has potential energy before it moves, and then as it begins to fall, it has kinetic energy. So our life is basically, from a scientific point of view, a series of energy transformations. Even us moving right now, we're converting the chemical energy in our food into motion and sound, hopefully not light, in our body. So in general, there's two types of energy, kinetic and potential, that everything falls under. So anything that's moving has kinetic energy. That's its own statement. And if you've taken physics, you know that kinetic energy is equal to 1/2 mass times velocity of the object squared. Potential energy, there's lots of different kinds. All right, it's basically stored energy. Okay, so anything that is kind of waiting to do a task has potential energy. And there's three examples here. Water being held behind a dam. As soon as the dam breaks, the water will flow. Okay, it has the potential to move. That's gravitational potential. Energy and chemical bonds. That energy is being ready. It's holding the atom together. So it's called chemical potential energy. It has the potential to react. And then lastly, if we hold two like charges near each other, they want to repel. So that's electrical potential energy. And an important facet of all of this is that the total energy of any system is equal to the sum of all of the different types of energies, which could be gravitational potential plus kinetic plus electrical energy plus chemical potential energy, and so on, whatever there is. All right, so the total energy is the sum of all the energies in a situation. And you may have seen this again. The change in energy of any system is equal to 0. So The initial energy it possesses is the same as the final energy. It appears to have a change sometimes because we lose it as light and heat. Okay, so a big facet of chemistry is the energy changes of the reactions we study. So thermochemistry is specifically the study of chemical and physical changes and their energy changes that are associated with it. When we study these two things, we have to understand two factors, the system and the surroundings. So the system is what undergoes the change. Usually that's the chemical reaction. Right? And then the surroundings are whatever is in contact with the system. But the key is here, whatever is changing is the system. And at the heart of that is essentially a chemical reaction somehow. And then the surroundings are whatever interacts with it to either give or take energy from it. And when we say energy, we're going to think of it as thermal energy or heat here in this unit. So there's three types of systems we have to consider. There's an open system where you can lose matter and energy. Okay, and think of this as a water bottle. So we'll call this an open water bottle. Right, if you tilt the bottle upside down, water falls out. That's the matter. If you leave the bottle in the sun, it heats up. Energy is being transferred. Okay. A closed system, we're going to jump to C here, is like a closed water bottle. Okay, the water can't fall out, but it can change temperature. So energy is transferred. And then lastly, an isolated system would be like a closed water bottle in a cooler. All right, or a thermos, for example. So the energy the matter, which is the water, can't get out, and the temperature generally does not change in a perfect situation. So there's three diagrams here to kind of describe those scenarios. All right, they're not in order. Really, if anything, we call that C and that B there, but the diagrams kind of describe what can happen. All right, so the system is the matter that's made up and is doing something, and then there are different types that we'll talk about. So the surroundings is anything in contact with the system that's not part of it. So very simply, there's a system, then there's everything else around that system, which combine to make up the universe. Now, if you're undergoing some kind of chemical change, the air around you can feel it, for example, but somebody 10,000 kilometers away will not. All right, so this statement here is true of the entire universe, but it's not practical for the study of chemistry. So what we're going to do is look at things that are in very close proximity to the reaction. So for example, a beaker that a reaction takes place in, your hand that's holding a reaction. We're not going to assume that the room is changing temperature because we look at things on a very small scale rather than large. Okay. So system and surroundings, right? There's an interaction between those two. So let's go through some examples. Identify the system and surrounding in each case, circle the system and underline the surroundings. So take a second to pause if you'd like to try this yourself. Right? And if you've done that, now we'll come back and go through the answers here. So remember that the system undergoes the change. That's the key to starting with identifying that in this scenario. So a pot of water boiling on a gas burner. Really, the gas burner is the system because it is undergoing the change, and the water is the surroundings because it is benefiting from the gas burner. The water doesn't boil unless it's absorbing the heat from the burner itself. Okay, so a log burns in the fireplace of a common room. So think about what's changing there. What's causing the change or the energy change? And in this case, it's the log burning. So I should include the log. All right, because it's burning. It's a combustion reaction. The common room warms up in the presence of the fireplace, so it's the surroundings. Okay, we don't say the entire world heats up because a fireplace is on in a certain room, which is why we're looking at a smaller scale here. And then a propane gas barbecue. Propane gas can undergo combustion, and then the barbecue itself is the surroundings, which takes advantage of that heat. Okay, so it's key to be able to identify what the system is and what the surroundings are in any scenario. A couple of terms that we need to go over. So thermal energy is the total quantity of kinetic and potential energy in a substance, which depends on the number of particles present. So it's the total amount of kinetic and potential energy. That means the more particles there are, the higher the total can be. All right, so basically it's just describing how fast all the particles are moving all together. All right. Heat describes the transfer of thermal energy. So we often use heat to describe something that's hot. It's technically incorrect. All right, so heat describes the movement of energy. So we wouldn't say that table is hot. You could say that table feels hot, right? Because it's describing you absorbing the heat from that table. So on a technical term, it's not actually a noun. Heat is not a thing. It's an action. It's the transfer of energy. And then lastly, temperature represents average kinetic energy of each particle in a substance. So notice how temperature and thermal energy are different. Okay, thermal energy of a sample is the total amount of kinetic energy. Temperature is the average kinetic energy of each particle. So if you have a sample of 10 particles, each with 10 joules of energy, right? Then you have a total of 100 joules. We've added that all together. But in terms of their temperature, they would average 10 joules each. Okay, so temperature is an average, not an added quantity. Now we know that we don't measure temperature in joules, we measure it in Celsius, but it's a relative term. So the higher the degrees Celsius or Fahrenheit, that means the higher the average kinetic energy of each particle in that sample. Okay, so that's just to differentiate some terms. We're going to use an example now to visualize that. A cup of water and a swimming pool are both at 25 degrees Celsius. So just assume it's a coffee cup and we've got a pool over here. Okay. So if you would like to pause and try this, describe their temperatures and thermal energies. So we'll say temperature and we'll say thermal energy relative to each other here. So pause, which one has more, which one has less, or are they equal? So hopefully you've paused and tried this. So in terms of the temperature, their temperatures are equal, right? We're told that they're both at 25 degrees Celsius. So what that means is each particle, right, has about the same amount of kinetic energy. Each particle has the average amount of kinetic energy the same, which means they're all moving at the same speed on average. There's always going to be some exceptions because we know temperature is not uniform. So it's equal for both. In terms of thermal energy, if they all have the same amount of energy, the particles, the fact that the pool has more particles means it has a higher amount of thermal energy in it because it's an additive property. So that's the difference between the two terms there. They can be at different temperatures, but have the same, they can be at the same temperature and have different thermal energies. All right, heat. We're getting more into what heat actually is. So it's represented by the symbol Q mathematically. Anytime you see this, we're talking about a transfer of thermal energy. Just think of a little fireball. When Q is positive, okay, so we'll say positive Q here. That means a reaction absorbs energy, okay, and we call it endothermic. An example of that is an ice cube. When an ice cube melts, it's absorbing heat from the surroundings, causing it to melt. When heat is negative, that means something is giving off thermal energy. So we can say here, giving off thermal energy. So we call that exothermic. Heat or thermal energy is being released from the system. All right. So just remember that mathematically because we'll do some calculations with that going forward. Now, chemically, you'll see heat as a reactant in an endothermic reaction, meaning add it. All right. And in an exothermic reaction, you'll see heat as a product, meaning it's released. Okay. After the reaction happens, there's some leftover thermal energy and it just gets released as heat, which we feel. Right, so those are energy changes of the two reactions. There's really nothing in between. Even if something doesn't feel like it changes temperature, there will be a small energy change associated with it. And whether it's positive or negative, we'll look at that mathematically. So theoretically, endothermic reactions okay, can be represented by these graphs here. So you see that it says a reaction has absorbed a net amount of energy into the system. So if we have this line here, right, we have the system separated by the surroundings. The system is taking energy from the surroundings. So if you think of it as your hand holding an ice cube, the ice cube takes energy from your hand, which makes it feel colder, and technically the ice cube warms up, which is why it melts, right? Now, in a more chemical sense of the word, right, we can look at this from here. So in the synthesis of nitric oxide, which is NO, the reactants, which are nitrogen and oxygen, need energy from the surroundings in order to form this bond here. They don't just form a bond when they bump into each other, because there's not enough energy to break their stable bonds. But if they take some energy from the surroundings, those bonds will break, right? It's like smashing two things into each other, but they're not moving fast enough, so you give them a little bit of extra energy, they smash, break their bonds, and reform as nitric oxide. So to do that, they store thermal energy from you, and it makes you feel colder. Right? Exothermic reactions are the opposite. So the best one for this is the burning of any fuel. So we've got ethane here as an example in a chemical reaction, and then in the graph we're using methane. So in any chemistry bench, if you've ever lit in the Bunsen burner, what you're doing is combining methane and oxygen. And if you've tried this, you know that nothing happens if you just turn on the gas and let it spew into the room. It stinks. What happens? You need to give it a spark, and then the energy gets released. The heat comes off of it. So the reaction releases energy, causes you to feel extra heat as it changes into its products. So it starts off with a certain amount of potential energy in its bonds, a total amount. After the reaction happens, okay, the products have a lower amount of energy, but we said that energy can't be created or destroyed, so that energy has to go somewhere. The difference here, right? So that means it gets released to the surroundings as thermal energy. So you have chemical potential energy in the bonds, you have chemical potential energy in the bonds. It's not the same, which means heat was either absorbed or released. So in this case, it was released. Right, so these graphs, just notice the axis here, it describes potential energy, right? And this is measured in joules. So we can make a note of that here. Okay. Really on the bottom here, it's that just, we don't say time, we say reaction progress, because time implies that we know the variables. But it's just from reactants to products going forward. And as it goes forward, the potential energy decreases, which means they lost energy to the surroundings. Right, so knowing how to read these graphs is important. It tells us whether something will absorb or release energy after a reaction. So here's a few examples. We're going to identify whether it's an exo or endothermic reaction. Okay, and we'll use these terms specifically. So ammonia gas condensing into a liquid. A gas to a liquid. Now, if you think about what happens there, gas is a high energy state. You have all these particles moving around, right? They're nice and spread out, and then a liquid has slower moving particles. So if the particles slow down, they must have lost energy, which makes it an exothermic process. Okay? They lost some form of thermal energy. Specifically, okay, there's other types of energy processes that we'll talk about, but this is specific to thermal energy and how fast everything's moving. Propane burning is a combustion reaction. It's a hydrocarbon burning with oxygen. That releases heat. Okay, so because it does that, we say that it's an exothermic reaction. Okay, we feel it getting hotter. And then lastly, if we look at the chemical reaction here, we see 560 kilojoules, right? And again, joules and kilojoules are how we measure energy. And because it's as a product, it means it was released. Therefore, this is an exothermic reaction. Okay? Even though the plus sign here just means it's one of the products. Okay, it's not saying that it's a positive value. It's just saying that there's energy coming out from the system from the reactants compared to the products. So lots of examples here. When we combine and split atoms, energy is released, and this is one of the ways that we actually generate our electricity. So nuclear fusion, which is not how we generate our electricity, is combining of two low mass atoms to form a heavier atom. This is the goal of energy production, right? And when they become stable, they release lots of extra energy, which makes them exothermic. Okay, so this energy that gets released, we would try to utilize for electricity, turning a turbine to generate electricity for our houses. Fission, on the other hand, is one that we do use, and that's the splitting of a nucleus. So common fuel is uranium, dangerous, and when it splits into two smaller atoms, and you might have studied nuclear reactions in grade 11, how the atomic numbers, right, of all of these need to add up to the atomic numbers of the reactants and products. Okay, so that's a whole other set of review, but if you add up on both sides, you have 1 neutron and 235 protons in uranium, right? And those will add up to give you the same value for those. So going forward from here, oh, and I guess just to correct that, it's the mass values that are on the top, not the number of protons. So the number of protons are on the bottom here, which is the atomic number. But in both cases, the top and bottom values are equal, which supports the conservation of energy. So even though it takes a large amount of energy to start this reaction, just to split the uranium atom, it's going to release an even larger amount of energy. So it's like a really good investment. You put some money in and you get a lot more money out. And that's the goal of these reactions, is to take the energy into useful forms. Okay, now on a less dangerous note, phase changes. Okay, so when substance changes phase, and remember that a phase change is just solid, liquid, and gas. Every substance will either absorb or release energy to do this. Substances going from higher energy states, like a gas, to a low energy state, will release energy. Just think of it as the particle calming down. Substances going from low to high energy states have to absorb energy. They need that little pick-me-up. They need extra energy to be able to separate from their intermolecular forces. So in the first example that you see here, right, of the water, it's going from solid to liquid. So ice to water. When ice melts, right, and it turns into a liquid, right, that's essentially what's happening here. Ice turning into water. So for that to happen, right, and we've got these the wrong way around here. Let's do this. Sorry for the mistake there. H2O. Let's just rewrite this for a second. Liquid turning into a solid. There we go. Right. So we'll just scratch out that example. It's inaccurate. So when water turns into ice, it needs to release energy to do that, right? Because the water as a liquid is too high energy for it to stand still. But when it releases energy, which makes it exothermic, okay, the particles they slow down. They're not moving as fast, which means they have less energy, and they stick together due to the intermolecular forces. And then on the other hand, to go to a higher energy state, so from water to steam or water vapor in this case, think of it like boiling a pot of water. You have to add energy to turn that liquid into a gas. So visually, here's a diagram that supports that, just showing that as we go from solid to gas, we have to add energy, and then as we condense a gas back into a solid, we remove energy to calm the particles down and slow them down in technical terms. So now let's just take a little application of this. And if we think about this, when we exercise and get warm, we sweat. So you have a person who's sweating. No eyes and nose there, just sweat. Okay, use the process of evaporation to explain how sweat cools us down. It's not the fact that you just have water on you absorbing the heat from you. So in terms of a process, okay, a process is like a chemical reaction. Okay, it's a reaction or a phase change. So chemical change is a reaction, phase change is a physical change. So what happens? Well, when we sweat, we want to cool down. So we want to bring down our body temperature. So to do that, we need to release energy. Well, for us to release energy, something has to absorb it. Okay. So in this case, ask yourself, who's the system here? Right? And who's the surroundings? Well, by having the water on us as sweat, liquid water. When water absorbs energy, it can go to a higher energy state, and it can turn into a gas. So by absorbing the energy from us, the system, which we're exercising and we're generating heat from cellular respiration, okay, so really us exercising is the burning of glucose. So we'll just jot that down here. Okay, and that's an exothermic process. Okay, every exothermic process needs to be paired with an endothermic process. So the heat from our body allows the liquid water, our sweat, to evaporate, and when it evaporates and it turns into a gas, it takes that energy with us and allows us to cool. So sweat, we'll put this in writing, sweat evaporating is an endothermic process. We can say it absorbs energy. Which results in our body temperature going down or cooling our body, giving us that effect there. Okay, so just to show you that it is really applicable in our lives. So we've seen these now once before. We're just going to formalize it, a potential energy diagram. You'll see these very often. We'll talk about the numbers that are here in the next lesson, but essentially I want you to pay attention to the graphs here. We have potential energy measured in joules or kilojoules. We have reaction progress, not time. We're not specifying time here because it's not a proper scale. And then we're showing what happens. So water vapor turning into liquid water is an exothermic process. It releases energy to slow down the molecules, and then the opposite is true. So the reverse of any phase change or any process is also the opposite energetically. So if the forward process is exothermic, the reverse process is endothermic, right? And we'll just pay attention to all of these. We've got the reactants on the left-hand side. We've got the products on the right-hand side. And then there's an arrow indicating if they're gaining or losing energy in between. So this just describes what was happening in those two graphs there. We've already said it. It's just stated there in words now. Okay, and that wraps up for here. It's just a summary of all the different terms. So it seems like a lot, but hopefully you have an idea and you're getting into the headspace of what energy is relative to chemistry. A couple of practice questions. Make sure we understand what thermal energy, heat, and temperature are and the differences. All right, thanks for watching, and hopefully that helped clear everything up.